Welcome, space enthusiasts, dreamers, and explorers of the unknown. Today, we embark on a journey through the incredible milestones of human space exploration. From our earliest observations of the cosmos to the groundbreaking achievements of the modern era, each step along this journey has brought us closer to understanding our place in the universe. Get ready to dive deep into the historical moments that have shaped space exploration as we know it. Every achievement we'll discuss is a testament to human curiosity, ingenuity, and determination to reach farther than ever before. So buckle up as we travel back to the dawn of astronomy and follow the trail of discovery to the stars. In 1610, Galileo Galilei used a telescope of his own design to make the first detailed observations of the night sky, revolutionizing astronomy. Through his observations of Jupiter's four largest moons, he realized these moons orbited a body other than Earth, which directly challenged the geocentric worldview. Galileo's observations of the phases of Venus directly challenged the Ptolemaic model, which held that Earth was the center of the universe. By showing that Venus orbited the Sun, Galileo supported the Copernican heliocentric model, radically altering humanity's understanding of the cosmos and laying the groundwork for observational astronomy. Isaac Newton's invention of the reflecting telescope in 1668 was a breakthrough in telescope design. Unlike earlier telescopes, which used lenses that suffered from chromatic aberration, Newton's telescope used mirrors to gather light. This new design allowed for clearer images and a more compact structure. Reflecting telescopes became the standard for astronomical research, enabling more precise observations of distant celestial objects and setting the stage for larger, more powerful telescopes in the future. In 1781, William Herschel discovered Uranus, the first planet identified with a telescope and the first new planet discovered since ancient times. This discovery expanded the known boundaries of our solar system and challenged the belief that only the planets visible to the naked eye existed. Uranus's discovery showed that telescopic technology could reveal previously unseen objects, prompting astronomers to search for other planets and celestial phenomena. Herschel's work inspired a systematic approach to planetary observation, advancing both planetary science and telescopic innovation. In 1801, Italian astronomer Giuseppe Piazzi discovered Ceres, the largest object in the asteroid belt. Initially thought to be a planet, Ceres was later reclassified as an asteroid and eventually a dwarf planet. Ceres's discovery led to the identification of the asteroid belt, revealing a new category of celestial objects. The study of Ceres and other asteroids has since provided insight into the solar system's formation, offering clues about early planetary building blocks. John William Draper captured the first telescopic photograph of the Moon in 1840. This was a major achievement in astrophotography, as it allowed astronomers to capture and analyze detailed images of celestial bodies. Prior to this, astronomical observation relied solely on sketches and written descriptions, but Draper's photograph offered a more objective, permanent record of the Moon's features. This advancement set the stage for photographing planets, stars, and galaxies, enabling scientists to study these objects in greater detail. In 1845, William Parsons, the third Earl of Rosse, used his massive telescope, the Leviathan of Parsonstown, to observe spiral structures in the Whirlpool Nebulae, known today as M51 or the Whirlpool Galaxy. His observations raised the idea that these structures could be other galaxies beyond the Milky Way. At the time, the nature of galaxies was not well understood, and Parsons' observations challenged the idea that the Milky Way was the entirety of the universe. This discovery hinted at the vast scale of the cosmos and helped inspire later studies in extragalactic astronomy. Scottish scientist William Leach was ahead of his time in 1861, proposing that rockets could be used for space travel. Though the concept of space travel was purely speculative at the time, Leach understood the potential of rockets to operate in a vacuum, unlike engines that require atmospheric oxygen. His ideas were far ahead of his time and provided an early theoretical basis for using rockets as a means of propulsion in space. Leach's proposal illustrated a visionary understanding of physics and inspired later rocket scientists like Tsiolkovsky, Oberth, and Goddard. In 1895, Russian scientist Konstantin Tsiolkovsky proposed the idea of a space elevator, inspired by the Eiffel Tower. He imagined a structure reaching from Earth to geostationary orbit, where an object could remain above a fixed point on the surface. While technologically unfeasible at the time, and still largely speculative today, the concept of a space elevator intrigued later generations of scientists and engineers, who continue to explore its potential for cost-effective access to space. Tsiolkovsky's 1903 publication, Exploration of the Universe with Rocket-Propelled Vehicles, provided the first rigorous mathematical treatment of space travel. He developed the rocket equation, which describes how the velocity of a rocket is affected by the rate of fuel consumption and exhaust velocity. Tsiolkovsky also envisioned using liquid oxygen and hydrogen as rocket fuels, proposing the concept of multi-stage rockets. His work laid the theoretical groundwork for modern rocketry, and his vision of space travel inspired future scientists and engineers. In 1914, Robert Goddard secured patents for two fundamental innovations: the multi-stage rocket and the liquid-fueled rocket. Multi-stage rockets would allow separate segments to detach once their fuel was spent, making it easier to achieve escape velocity without excess weight. Liquid-fueled rockets offered greater control and power compared to solid fuels, enabling efficient, sustained thrust. Goddard's patents marked a major step toward practical rocketry, laying the groundwork for future space launches. In 1917, Dutch astronomer Adriaan van Maenen observed a candidate for what we would now recognize as an exoplanet orbiting Van Maenen 2. At the time, the technology and understanding of exoplanets were limited, so this observation wasn't fully appreciated. However, it suggested that planetary systems might exist beyond our own, a notion that would fuel much later exploration. Hermann Oberth's thesis, initially rejected but later published as By Rocket into Planetary Space, laid out key principles for spaceflight. Oberth argued that rockets could be used for interplanetary travel, covering everything from propulsion to energy requirements. His work profoundly influenced European rocketry, inspiring scientists like Wernher von Braun. Oberth's research provided technical insights that would later enable controlled space travel. On March 16, 1926, Robert Goddard launched the first liquid-fueled rocket, reaching an altitude of 41 feet. This launch, though modest, demonstrated the feasibility of using liquid fuel for controlled propulsion. Goddard's innovation enabled greater power and precision than solid fuel rockets, a crucial breakthrough that made spaceflight possible. Liquid-fueled rockets would later become the mainstay of space exploration, from lunar missions to interplanetary travel. Karl Jansky, an engineer at Bell Telephone Laboratories, detected radio waves from the center of the Milky Way in 1933. His discovery marked the birth of radio astronomy, a field that allows astronomers to study celestial objects through radio frequency emissions. Radio astronomy has since revealed phenomena invisible to optical telescopes, including pulsars, quasars, and cosmic microwave background radiation, providing insights into the structure and origins of the universe. On June 20, 1944, a German V-2 rocket reached an altitude of 189 kilometers, crossing the Kármán line and entering space. The V-2 was the first human-made object to reach space, demonstrating that powerful rocketry could overcome Earth's gravitational pull. Though developed for wartime purposes, the V-2 technology laid the groundwork for post-war advancements in space exploration, as both the U.S. and Soviet Union seized V-2 technology and recruited German engineers, including Wernher von Braun, to jumpstart their own space programs. In 1957, the Soviet Union launched Sputnik 1, the world's first artificial satellite, sparking the start of the space race. Sputnik's simplicity, an 83.6 kilogram sphere with 4 antennas, belied its impact. The satellite's radio pulses could be tracked across the globe, creating a moment of awe and concern as nations realized that space was within reach. Sputnik's success demonstrated the Soviet Union's advanced rocketry and fueled American efforts to catch up, prompting the United States to form NASA in 1958. Sputnik marked the beginning of humanity's entry into space, making it clear that space would be a new arena for scientific discovery and national rivalry. The Soviet Union's Luna 1 mission in 1959 was originally intended to impact the Moon, but instead became the first human-made object to reach heliocentric orbit after it missed the Moon. Although it failed to achieve its primary objective, Luna 1 collected groundbreaking data about the solar wind, the stream of charged particles emitted by the Sun. Before this, scientists theorized about the solar wind, but Luna 1 provided the first direct measurements, advancing our understanding of solar-terrestrial interactions. This information was crucial for planning future missions, as solar wind affects spacecraft and communication systems. On April 12, 1961, Soviet cosmonaut Yuri Gagarin made history aboard Vostok 1, becoming the first human to orbit Earth. This 108-minute flight confirmed that humans could survive and work in space, a significant unknown at the time. Gagarin's mission cemented the Soviet Union's lead in the space race, creating a cultural icon and inspiring millions worldwide. His orbital flight reached a maximum altitude of 327 kilometers, with Gagarin famously reporting, "I see Earth. It is so beautiful." This mission also emphasized the need for rigorous astronaut training, as Gagarin had to handle extreme forces, weightlessness, and re-entry, surviving an ejection from the capsule at 7 kilometers above Earth. NASA's Mariner 2 became the first successful planetary flyby mission when it reached Venus on December 14, 1962. This milestone marked humanity's first close-up exploration of another planet. The spacecraft measured Venus's surface temperature at approximately 425 degrees Celsius, 797 degrees Fahrenheit, confirming the planet's intense heat, and it studied Venus's thick atmosphere. Mariner 2's data helped dispel hopes that Venus might harbor life and contributed to our understanding of greenhouse effects. Mariner 2's success demonstrated that interplanetary exploration was possible, setting the stage for future planetary science missions. On March 18, 1965, Soviet cosmonaut Alexei Leonov performed the first spacewalk, or extravehicular activity, EVA, during the Voskhod 2 mission. Leonov's 12-minute spacewalk was a high-risk maneuver, as his spacesuit expanded in the vacuum of space, making it difficult to re-enter the spacecraft. He eventually managed to squeeze back inside by manually venting air from his suit. Leonov's spacewalk was a historic moment, demonstrating that astronauts could work outside their spacecraft, an essential skill for tasks like assembling space stations, performing repairs, and conducting science experiments. The Soviet Luna 9 became the first spacecraft to achieve a soft landing on the Moon on February 3, 1966. Previous missions had either impacted the surface or missed the Moon altogether, so Luna 9's controlled descent represented a major technical achievement. It transmitted panoramic images from the Moon's surface, proving that the surface could support a lander without sinking, a concern based on theories that the Moon was covered in a thick layer of dust. This mission gave humanity its first direct view from another celestial body and demonstrated that soft landings were achievable, a crucial step for future crewed lunar missions. NASA's Apollo 11 mission, which landed on the Moon on July 20, 1969, was a defining moment in human history. Astronauts Neil Armstrong and Buzz Aldrin became the first humans to walk on the lunar surface, while Michael Collins piloted the command module in orbit. Apollo 11 achieved a complex set of maneuvers, from lunar orbit insertion to descent and ascent from the Moon's surface and return to Earth. Armstrong's famous words, "That's one small step for man, one giant leap for mankind," encapsulated the mission's significance. Apollo 11 showcased human ingenuity, courage, and perseverance, achieving President Kennedy's 1961 goal to land a man on the Moon and return him safely to Earth. It also provided valuable lunar soil and rock samples, offering insight into the Moon's geology and the formation of the solar system. In 1971, the Soviet Union launched Salyut 1, the world's first space station. Salyut was designed to allow cosmonauts to live and work in space for extended periods, testing human endurance in microgravity and laying the groundwork for long-term missions. Although the first crewed mission to Salyut 1 ended in tragedy when the returning cosmonauts perished, due to depressurization during re-entry. The station demonstrated the feasibility of sustained space habitation. Salyut 1 was a pioneering step in developing space infrastructure, eventually leading to more advanced stations like Mir and the ISS. NASA's Viking 1 and Viking 2 missions, which landed on Mars in 1976, were the first successful attempts to operate on the Martian surface. The Viking landers conducted biological experiments, searching for signs of life, and provided high-resolution images of Mars. Although no definitive signs of life were found, the Viking data offered new insights into Mars's soil composition, atmosphere, and weather patterns. These landers paved the way for future Mars exploration by proving that robotic missions could survive on Mars and send valuable data back to Earth. The Space Shuttle program, beginning with the launch of Columbia on April 12, 1981, introduced reusable spacecraft to space exploration. Unlike traditional rockets, the shuttle could launch into orbit, return to Earth, and be refurbished for subsequent missions. The shuttle program enabled a new era of orbital activities, from deploying satellites to servicing space telescopes like the Hubble. The program also advanced microgravity research, as the shuttle's payload bay could carry science experiments and laboratories into space. Although the shuttle program faced significant challenges, including the tragic Challenger and Columbia disasters, it contributed immensely to space exploration by supporting the development of the ISS and facilitating an era of frequent human space missions. The Soviet Mir space station, launched in 1986, was the first modular space station designed to grow over time with the addition of new modules. Mir hosted international crews and advanced research in microgravity, setting records for long-duration human spaceflight. Mir demonstrated the feasibility of complex orbital structures, with scientists and engineers solving problems in real time and conducting critical biological and physical sciences research. The lessons learned from Mir's construction and operation were instrumental in planning and building the International Space Station. In 1990, NASA launched the Hubble Space Telescope into low Earth orbit, opening a new chapter in observational astronomy. Positioned above the Earth's atmosphere, Hubble provided images of unparalleled clarity, capturing details impossible to achieve from ground-based telescopes. Hubble's discoveries have included the accelerated expansion of the universe, confirming the existence of dark energy, mapping galaxies in the early universe, and identifying thousands of exoplanets. Hubble has also delivered iconic images, from the Pillars of Creation to the Hubble Deep Field, revealing the vastness and diversity of the cosmos. The International Space Station, launched in 1998, welcomed its first permanent crew in 2000, marking the start of continuous human presence in space. The ISS was built through a collaboration between NASA, Roscosmos, ESA, JAXA, and the CSA, among others. As a microgravity research laboratory, the ISS supports scientific experiments in biology, physics, astronomy, and materials science. Research aboard the ISS has direct applications on Earth, from advancing medical research to improving environmental monitoring. The station has also provided critical insights into the effects of long-duration space travel on the human body, essential knowledge for future missions to Mars and beyond. Launched in 1997, the Cassini-Huygens mission reached Saturn in 2004, becoming the first spacecraft to orbit the planet. Cassini conducted detailed studies of Saturn's rings, atmosphere, and magnetosphere, while its Huygens probe landed on Titan in 2005, marking humanity's first landing on a world in the outer solar system. Cassini's observations revealed active geysers on the Moon and Enceladus, suggesting a subsurface ocean that might harbor life. Huygens' descent provided unprecedented data on Titan's atmosphere and surface, revealing rivers and lakes of liquid methane and ethane. The mission's findings expanded our understanding of planetary systems and the potential for life in the outer solar system. India's Chandrayaan-1 mission, launched in 2008, marked India's entry into lunar exploration. Chandrayaan-1 orbited the Moon, mapping its surface composition, and made a significant discovery: the presence of water molecules in the lunar soil. This finding challenged long-standing assumptions that the moon was completely dry and suggested that water ice might be present in permanently shadowed craters at the lunar poles. The discovery of lunar water reinvigorated interest in the moon and underscored its potential as a resource for future crewed lunar missions. In 2010, the Japan Aerospace Exploration Agency, JAXA, launched Icaros, the first spacecraft to successfully demonstrate solar sail technology in interplanetary space. A solar sail works by capturing solar radiation pressure, a method of propulsion that requires no fuel, allowing for sustained acceleration over long distances. Icaros proved that solar sails could maneuver and generate power from sunlight, a promising technique for long-duration missions where fuel limits are a major concern. This success inspired further research into solar sails, positioning them as a potential propulsion system for missions to outer planets and beyond. In 2012, NASA's Curiosity rover landed on Mars, marking one of the most advanced robotic missions to the Red Planet. Curiosity, part of the Mars Science Laboratory mission, was equipped with a suite of scientific instruments designed to analyze the Martian surface, atmosphere, and geology. It discovered evidence of ancient riverbeds, confirming that Mars once had liquid water on its surface, and found complex organic molecules in the soil, essential building blocks for life. Curiosity's findings suggested that ancient Mars could have supported microbial life, a tantalizing hint in the search for life beyond Earth. The mission also tested technologies like the Sky Crane landing system, an innovation that has since become essential for landing heavy payloads on Mars. The European Space Agency's Rosetta mission, launched in 2004, made history in 2014 by successfully orbiting and landing on a comet, 67P/Churyumov-Gerasimenko. After a decade-long journey, Rosetta deployed the Philae lander, which made a dramatic descent and became the first probe to land on a comet. Though Philae's landing was challenging, its harpoons failed to anchor, causing it to bounce. Its instruments managed to transmit data on the comet's surface composition, including complex organic molecules. Rosetta's close-up study of cometary activity provided unprecedented insights into comet formation, the early solar system, and the role comets might have played in delivering organic compounds to Earth. This mission was a technical and scientific triumph that deepened our understanding of these ancient bodies. In July 2015, NASA's New Horizons probe made the first-ever flyby of Pluto, offering humanity its first close-up view of this distant dwarf planet. New Horizons revealed that Pluto, far from being a static, frozen body, has a diverse and geologically active surface. It observed mountains made of water ice, plains of nitrogen ice, and a thin atmosphere. The mission also discovered signs of possible internal heat sources and cryovolcanoes, which release icy water rather than molten rock. These findings transformed Pluto from a distant point of light to a dynamic, complex world, expanding our understanding of the outer solar system and Kuiper Belt and reshaping the way we think about dwarf planets. In December 2015, SpaceX achieved a critical milestone in reusable rocketry with the successful propulsive landing of the Falcon 9 first stage. After delivering its payload to orbit, the rocket's first stage descended back to Earth, performing a controlled landing. This development was revolutionary because it opened the door to significantly reducing the cost of launching payloads by reusing rocket components, which had traditionally been discarded after each launch. SpaceX's reusable rocket technology has since transformed the commercial space industry, reducing launch costs and making regular access to space more sustainable and affordable. On September 14, 2015, and announced in 2016, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time. These waves, produced by the merger of two black holes, confirmed a key prediction of Einstein's general theory of relativity. Gravitational waves provide a new way of observing the universe, allowing scientists to detect and study events that do not emit light, like black hole mergers. This breakthrough opened an entirely new field of gravitational wave astronomy, enabling researchers to study the cosmos through these ripples in space-time, providing insights into the dynamics of massive celestial objects. In 2019, the Event Horizon Telescope (EHT) project achieved a remarkable feat by capturing the first direct image of a black hole located in the galaxy M87. This black hole, with a mass of about 6.5 billion times that of our Sun, was imaged by synchronizing a network of radio observatories around the world to act as a single Earth-sized telescope. The image revealed a bright ring surrounding a dark central region, the shadow of the black hole's event horizon, providing visual confirmation of the existence of black holes and supporting Einstein's predictions about their appearance. This image was a milestone in observational astronomy and confirmed fundamental aspects of theoretical physics. In 2021, NASA's Perseverance rover and its companion, the Ingenuity helicopter, landed on Mars as part of the Mars 2020 mission. Perseverance was designed to search for signs of past microbial life and to collect samples for potential future return to Earth. One of its main tasks is drilling into Martian rock to cache samples that could provide conclusive evidence of past life. The mission's Ingenuity helicopter was a technological marvel, performing the first controlled flight on another planet. Ingenuity's successful flights demonstrated that aerial exploration is feasible on Mars, offering a new dimension to planetary exploration. The technology used on this mission is expected to play a crucial role in future crewed Mars missions, supporting both scientific research and logistical operations. Launched on December 25, 2021, the James Webb Space Telescope, JWST, is the most powerful space telescope ever constructed. Operating primarily in the infrared spectrum, JWST is designed to observe some of the oldest galaxies and stars in the universe, potentially seeing back to the epoch of reionization when the first stars were born. With its advanced optics and large mirror, JWST can peer into dense star-forming regions and analyze the atmospheres of exoplanets, searching for signs of habitability and even potential biosignatures. The telescope's capabilities will enable astronomers to study phenomena across a vast range of scales, from our solar system's planets to the earliest galaxies, promising transformative discoveries in almost every field of astronomy. In 2022, NASA's DART, Double Asteroid Redirection Test, mission marked the first time humanity intentionally altered the trajectory of an asteroid, Dimorphos, in a demonstration of planetary defense. The mission's objective was to test whether a kinetic impactor could change an asteroid's orbit, providing valuable data on methods for potentially preventing hazardous asteroids from impacting Earth. DART's success was confirmed by measuring a change in Dimorphos's orbit around its parent asteroid, Didymos, proving that kinetic impact is a viable method for asteroid deflection. This mission's success is a significant step toward protecting Earth from potential asteroid impacts. India's Chandrayaan-3 mission, launched by the Indian Space Research Organization (ISRO), became the first to successfully land at the Moon's south polar region, a key area for future lunar exploration due to its potential water ice deposits. The presence of water ice at the poles could support future lunar bases, providing a source for drinking water, oxygen, and even rocket fuel. Chandrayaan-3's success highlighted India's growing capabilities in space exploration and contributed to humanity's knowledge of the Moon's polar regions, making it a vital step toward establishing a sustainable human presence on the Moon. In 2024, SpaceX's Starship achieved a significant milestone by performing the first successful in-space propellant transfer. This technology is crucial for deep space missions, allowing spacecraft to be refueled in orbit and enabling sustained missions to the Moon, Mars, and beyond. The in-space refueling capability is a cornerstone of SpaceX's plans to establish a self-sustaining human presence on Mars. By reducing the amount of fuel needed for launch and allowing for refueling en route, in-space refueling makes it feasible to carry more cargo or reach destinations farther than previously possible. This demonstration is a step toward a future where human exploration extends to the entire solar system. From Galileo's telescope to landing probes on distant comets and capturing images of black holes, each milestone in space exploration has brought us closer to understanding the universe. Every breakthrough builds on the work of countless scientists, engineers, and explorers, fueling our quest to reach farther and learn more. As we look to the future, ambitions for interstellar exploration, lunar colonies, and Mars settlements grow stronger. Humanity's journey into space has only just begun, and with each step forward, we redefine what's possible. The stars await. Thank you for watching. Don't forget to give it a thumbs up and subscribe for more space content and NASA news.